Hello and welcome to another episode of The Elements of Deep Sea Mining. I'm Eric Young. Today's episode is part one of a two-part series with Lyle Trytten. You might recall that we've already released part two of this series over a month ago. Lyle is a nickel and cobalt industry expert with over 30 years of experience in engineering, R&D, project evaluation, and sustainability. Through Trytten Consulting Services, Lyle now advises major industry development projects, governments, and international agencies on topics related to mineral infrastructure build-out. I first met Lyle when I was working on my master's research about the global nickel supply chain. A mutual friend introduced us, describing him simply as a retired chemical engineer from Sherritt International. At the time, I would regularly call Lyle to ask questions about nickel processing and supply chains, assuming he was just a retired engineer generously helping out a curious graduate student. It gradually dawned on me, especially when I noticed how others in the nickel space knew and referred to Lyle with deep respect and recognition, that I was actually dealing with one of the field's leading experts. So naturally, when I had questions about mineral supply chains for this podcast, particularly around the real environmental and social impacts, I reached out to Lyle again. And as usual, he's been generous with his time. In today's episode, Lyle puts context around ESG aspects related to deep sea mining, giving a short explainer on where impacts happen in mineral supply chains.
What does ESG mean? It means environment, social, and governance. And we need to tear this apart to think about the impacts, just like we tear apart rocks to get the minerals we want.
So please stick around, because understanding these nuances is key to making informed decisions about the future of critical minerals. Okay, welcome to the Elements of Deep Sea Mining. I'm Eric Young. With me today is Lyle Trytten, the nickel nerd and world-renowned expert in all things nickel processing, as well as general sustainability and mineral sector knowledge. So thanks for coming, Lyle.
Oh, you're very welcome, Eric. It's a pleasure to be here.
Yeah, so I will have introduced you earlier, but let's start with your background and where you come from. This episode is going to be a mix of mineral processing and Canada relevant topics, and so you can start with where you're from and what you do, and why people should take you as an expert on all of the things you're going to discuss.
Sure. Thanks, Eric. So, I'm an Alberta boy in Canada. As you can tell from the sweater, I have a Norwegian heritage, settlers that came in the late 1800s into the U.S. and up into Canada and homesteaded and eventually built what is now Canada on the traditional territories. I live in Edmonton, which is treaty territory here in Alberta. I've had the good fortune of building a really interesting career over the last 30 years. But as an Alberta boy, born and bred, did chemical engineering at the University of Alberta, I expected to spend my career in oil and gas. I did a master's degree focused on heavy oil processing. But, that industry is pretty up and down, and I managed to graduate with my master's in a down period and ended up not working in heavy oil. Initially, I worked in some food processing stuff, playing around with supercritical carbon dioxide, which has suddenly become relevant again now, 30 some odd years later, doing some heavy oil work as well on the R&D level. And then eventually I found a role at Sherritt International in Fort Saskatchewan, which is a metals processor, knowing nothing about the metals industry. I went there and it was starting over from ground zero, and that was fine. And I thought, we'll see how this is for a couple of years, and then I'll decide what I really want to do with my life. And 25 years later, after having done R&D, greenfield project engineering for metallurgical projects around the world, plant startups, brownfield engineering, detailed engineering for brownfield projects in operating facilities, fertilizers, hydrogen, utilities, metals, all kinds of different things, nickel, copper, cobalt, zinc, refractory gold, startups in foreign jurisdictions. I had a very wonderful career, environment and sustainability roles. And after 25 years, I decided that I'd had enough of the corporate life and decided to launch my own company. So I now offer my consulting services widely, mostly, bringing that broad base of experience to bear on, project evaluations of different types. Helping clients bring good projects forward is how I like to think of it. A couple of years ago, a colleague of mine tagged me as the nickel nerd. And I thought, you know what? I can own that. I'm pretty nerdy about what I do. And there aren't a lot of independent experts out there in the nickel business. It's a very close knit community, mostly working for, a handful of companies in the world. And so there's lots of people that know more, but they're tied to some corporate master. And I'm not. And I love the ability to be able to speak my mind, tell people what I really think about things.
So you described being all over the world and all over different sectors. I didn't realize that you had spent so much time outside of nickel specifically. And was that also sort of with your Sherritt hat on?
Yeah, absolutely. Sherritt was a fantastic company to learn the metallurgical processing industry at. Not only did they have the nickel and cobalt refinery with an attached fertilizer complex here in Alberta, and for those of you from Alberta, that was the start of the industrial heartland area that now has, a couple of dozen large producers. Sherritt started there in 1954 with the nickel refinery, and that bred everything else. But they then developed a metallurgical consulting and technology sales business, leveraging their hydrometallurgical expertise, and developed processes for hydromet processing, pressure leaching of zinc concentrates, refractory gold concentrates, uranium, a bunch of other things. And that's, through them, I got exposed to a lot of international projects. I helped did some of the initial conceptual design and mass and energy balance work for what is now the Minera Resources project in Australia. I spent a year there starting that facility up. Got to design a pressure leaching circuit for copper anode slimes in Indonesia and got to go and start that one up. That was a fascinating experience. A base metals refinery in the US. I worked on a project in Madagascar. I've been in South Africa, Brazil, Chile, Argentina, Mexico, a bunch of other places. Not all for projects that ended up going ahead, but I've been in a bunch of different types of metallurgical operations across the world and seen how things are sometimes done a little bit differently. We get a North American and Western European bias to how we do things, and it's important to realize that there's other ways.
And then you ended up before you left Sheridan, you were their chief sustainability person in the company. So how did you get from kind of being very technical into taking that lead role in the sustainability side?
Well, as a technical person, you develop the ability to understand a wide range of issues, and especially coming from a chem-eng background, what I think of more broadly as process engineering. You think about process flow, what goes in, what happens to it, what comes out, and that includes not just, making your product, but also emissions. So, when I was running the engineering and R&D groups, I got handed the environment group at one point. Here, run this too, which was an interesting experience. The group didn't know I was coming in until they saw me in a conference room with their previous manager no longer on site. And, I picked up the environment group, and then I started getting into the regulatory world and doing government relations. And that ended up with, us rejigging the company a little bit. And I was the lead sustainability person, not for the whole company, because we had multiple sites, but certainly for the Fort Saskatchewan site, which meant I was helping do, annual sustainability reports and all that sort of thing, as well as, EH&S on site, emergency response, all those kinds of things. And that very wide background from detailed design all the way through to government relations and everything along the way has given me a very good overview of the entirety of our business.
And I mean, you mentioned it, but this is kind of where you try to focus now, is both the sustainability and the technical processing side of things. Certainly what you write about in your public briefs and one pagers and white papers, etc. So you're still very much in this taking technical expertise and applying it to the sustainability kind of lens, right?
Absolutely. Part of what the practice I do right now is I help companies with reviews of projects. You need to understand what you're getting into if you're going to acquire a project. How is it going to operate? But also, what are the broader considerations around it? If you have an effluent, what does it look like? Where does it go? How is it managed? Does the project make sense? What are the pros and cons? Because you don't want to be surprised by something that you find out later. I do, technical reviews of life cycle analysis studies, and it's really important to make sure that, an LCA is done with credible data going in, right? If the mass balance doesn't work, if the study practitioner has not included all the relevant reagents and outputs, there's a problem, and it's got to be found and called out before it gets published. And so, I work on those kinds of things. I help do lead engineering studies that are all encompassing. So one of my clients has done a preliminary economic assessment and pre-feasibility study for a major nickel project here in Canada, and I led the engineering teams through all of that. Third-party teams, but it's always with a focus on the overall project and overall impacts. I'm not a specialist in mining, far from it, but I know enough about mining to know where the issues occur.
Okay, great. So then I guess I'll just kind of describe where I hope we'll go in this conversation. So, since I started this podcast, and this is probably, by the time it comes out, episode 6 or 7, I had always thought that I would eventually reach out to you on the processing, refining side of the deep sea mining question, because it seems like a lot of people kind of like me with superficial understanding of mining and minerals, they kind of put deep sea mining up against land-based mining, thinking kind of mine-to-mine comparison. And what I've learned to think about in the past few years is kind of that the mine is only the starting point, and then there's all this processing, and it seems like a lot of the impacts come from the processing. So I hope that, so I'm going to ask you to kind of get into the downstream aspects and hopefully explain to people like me who haven't really thought about this, how mineral processing and refining works. But the reason that I reached out to you kind of so early on is because, like you, I'm from central Canada, and the news that I follow right now is all about how the tariffs coming out of the new administration in the US are going to have big impacts on Canadians. And so I started having questions about how this affects the mining industry, given that Canada is a very large mining, not only kind of domestic mining, but internationally, a lot of mining companies are located in Canada for some reason, which I've always kind of wondered why Canada has ended up being such a dominant player. And so I was looking for someone to reach out to kind of discuss how these tariffs are going to affect the Canadian and American minerals industry, et cetera. So I hope that we can kind of get into all of these things. But let's start with mining and processing and refining. So for a general uneducated audience, can you kind of discuss the differences between mining, processing, refining, and just give us an overview of how that works?
Sure. So, we have a long supply chain to go from what's in the ground to the things that are in your hands, your smartphone, your computer, your tableware, whatever it is that's made of elements, right? And the old line in the mining industry is, if it's not grown, it's mined, right? So we make a lot of things out of, wool from sheep, cotton, timber, etc. But those are all those organic products are one end, but there's a lot of what we make that comes out of metallic elements. And a lot of what we mine is non-metallic things that go into construction, gravel, aggregate, that kind of thing, as well as into the agricultural process. So we mine fertilizers, we mine fossil fuels. So the mining process is the process of getting the thing you want out of its native environment. So if you're digging up rock, you got to get it out of the ground. For the deep sea mining side of it, you got to pick nodules off of the ocean floor and get them to surface. That's mining. That gets you what we call an ore out of the environment into something you can do with it. And on terrestrial mining, that usually involves stripping away material that's in the way. Often that's some vegetation and some overburden, as well as waste rock that is not valuable to you, that is in the way of getting to the stuff you want, which is what we call ore. And we have different types of mining processes on land. We have, surface access mines, like strip mines used for coal. So, anybody in Germany will be very familiar with the strip mines for coal there, certainly in the prairies of Canada, in the US. That's how coal is usually mined. There's a few underground coal mines in the world, but they're not the dominant source. So those are strip mines. They tend to be shallow but large horizontally. Right, so they might be 10 meters deep or 20 meters deep or 30 meters deep, so they're not hundreds of meters deep. Then we have pit mines, open pit mines, which are very deep horizontally sometimes. They can be hundreds of meters, but they tend to be a more confined surface area footprint because what you're doing is chasing an ore that is going down into the ground. And so you're removing stuff to chase usually a pipe of ore that you want to dig. And so as you make a cone down around it, you remove a lot of waste rock to follow this narrow pipe that you're going down. The more waste rock you have to remove, the more waste rock you have to deal with, the more expensive it is. But if your pipe is good quality, then it can pay for it. And then you get into underground mining where that pipe might extend far, far underground. And we have mines in Canada and South Africa that are, now thousands of meters deep, kilometers into the earth, where they're chasing a very high grade ore. Underground mining is expensive, but it can be worthwhile when the ore is super high grade. So we've got all these different types of mines, but all deal with the same issues. You have waste that you don't want, get rid of it as soon as you can. Then you have ore that you do want. But the ore is almost always a mixture of minerals, of which you want some and you don't want others, because that's what Mother Nature left you in the ground. If you're into coal mining, you'll clean the coal. If you're into gravel mining for aggregate for construction, you'll do a screening to separate that. But it's all, broadly speaking, what we would consider ore in the business. Once you have that ore out of the ground, then you move into the mineral processing realm, which is where we look to take the rock apart and recover the minerals that we want. So a mineral is just a chemical combination. It's molecules structured into mineral grains of different elements. So, you might have, common ones are pyrite, which is iron sulfide, one iron, two sulfur atoms in a structure. You've also got pyrrhotite, which is one iron and one sulfur. Nominally, it's not quite 1-to-1. It's a different iron sulfide. It's a different grain structure, and you can recover them separately from each other in some instances. Copper occurs in, a dozen or more minerals. Nickel occurs commonly in about 3 or 4 minerals. All of these metals that we want to recover occur in multiple forms, but very rarely are we mining something that is a native element, right? You find that in gold sometimes. Gold panners, they're recovering native gold. You sometimes find platinum that way. We used to find copper that way. The First Nations in North America were mining native copper in Michigan thousands of years ago, right? It was sitting there on and in the ground as sheets of copper. You don't find
sheets of copper, not just nuggets of copper.
Not just nuggets, large structures that had formed over time by the aggregation of copper from fluids. That was the easy stuff to mine, right? Now we're into the hard stuff, right? Which is why mineral processing becomes so much more important, to get the minerals you want away from the minerals you don't want. When we do that mineral processing, whatever that process is, and there's a number of them like froth flotation and screening and gravity separation and magnetic separation, we're trying to recover a mineral we want from a bunch of other stuff. Pretty typically, a base metal mine or a gold mine will be more than 98% stuff you don't want, which is, a fairly astounding value, which is why you end up with tailings. Tailings are the rest of the material from that first separation process to get the material you want away from the material you don't want. What you don't want is what we call tailings. And you make in that process a more concentrated form of the minerals that you want, not of the metals yet. So you would maybe recover pentlandite, which is a nickel iron sulfide, as a mineral concentrate, maybe 10% nickel, maybe 20% nickel, but it's not pure yet. But everything else would get left behind as the tailings deposit. And of course, depending on the host rock, those tailings can look very different.
Yeah. Okay. So you start with the ore in the ground. You dig that up, and generally, I'm only kind of familiar with nickel, but people talk about nickel as being kind of between 2% and 0.2% of that ore body. But you're saying that through concentration, you would eventually get kind of the first processed ore to be upwards of 10% before you send that off to be refined, I suppose.
Right. If you've got a nickel ore body at 1%, you could ship that ore. It's technically viable, but it's very expensive to ship, 100 parts of crap with 1 part of good stuff, right? So you don't really want to do that. So if you can find a way to avoid shipping the entirety of the ore body to a processing facility, then you do that. There are times where we ship the entirety of the ore body, and this is very common in the nickel business. We have nickel sulfides that we can concentrate by mineral processing, but nickel oxide ores, the nickel laterites common in Indonesia, New Caledonia, Cuba, the Philippines, these are not able to be concentrated by the means that we use for other, like typically sulfide host rocks. And so you end up taking that entire ore body and effectively skipping the mineral processing stage and going straight into the refining stage. So the refining stage can also comprise a number of processes, but is where you take that mineral concentrate, or in rare instances, the whole ore body, and then treat it intensively through processes like smelting and leaching and electrolysis to recover the specific metals that you are after, right? So we make nickel cathode or nickel briquettes, and we make cobalt cathode and copper cathode. Sometimes you'll make a byproduct that is still a mixture of things, like a nickel mine like Glencore runs in Sudbury or at Raglan that makes a nickel concentrate that they smelt in Sudbury that then makes a nickel matte that goes to Norway for refining at the Nickelverk refinery. Will make nickel, cobalt, and copper metals. But there'll also be a PGM concentrate, platinum group elements, platinum, palladium, osmium, ruthenium, iridium, etc. I always miss one. That then goes to a specialized refiner to make all of those individual metals. So we make a mixture
let me
of
just
things.
before we get super deep into refining, I just want to understand better the tailings picture. So tailings is, I don't think that a lot of people actually know what a tailings comprise of. We know that every once in a while we hear about a tailings dam that breaks, and then there's something that floods out into a nearby river. But so tailings is that essentially that first rejected part of the ore body that doesn't make it from the processing stage to the refining stage. So then why are they often in liquid form? Are they always in liquid form? And why are they not just a pile of ore that can go back down the hole and be inert?
Well, they're generally, I wouldn't say in liquid form, I would say in slurry form, just to be pedantic about it. Slurry being a mixture of solids and liquids. And that material is, basically whatever the host rock was, right? It's what's left over after you get out what you want. So it depends on your ore type, right? So, the project that I've been working on in northern BC, the nickel project, the ore type is olivine and peridotite, which are magnesium silicates with nickel in there as pentlandite grains. There's a little bit of extra sulfur that ties up some iron as pyrrhotite. So effectively have some pentlandite, some pyrrhotite, and a whole bunch of magnesium silicates. The total sulfur is 0.4, 0.5%. So 99.5% of the ore body is not the sulfur minerals, or 99% broadly is not.
And the sulfur minerals is where the nickel is, and that's what you're after.
The nickel that we can recover is in the sulfide minerals. There's some nickel in those host rock minerals as well, and in minerals are never completely pure, or rarely, because atomically Mother Nature leaves us messes to deal with, right? We love her for trees and plants and fuzzy animals. But when we're dealing with stuff in the ground, for example, the magnesium silicates will have 0.1% nickel in the magnesium silicate matrix, substituted for the magnesium in that grain matrix. And that's very, very difficult to recover. Technically doable. You pour enough acid on it, you can get it out, but it's economically not suited to that recovery. So we recover the ones that are easy to recover, leave everything else behind. So if you have an ore body for which effectively the tailings are magnesium silicates, those are pretty benign. They in fact have some beneficial characteristics. They react naturally with CO2 from the atmosphere, suck it up and sequester it as mineral carbonates. That's good. There's a little bit of remnant sulfur that could potentially leach and make sulfuric acid, and that's not good. But that's probably going to get neutralized by the magnesium silicate rocks, which are basic in nature. But if you have a deposit that has a very high sulfur content and you're rejecting a bunch of iron sulfides, and so, for example, the Kevitsa mine that Boliden runs in Scandinavia, after they've recovered their copper and nickel sulfides, they then actually run a separate flotation process to recover the high sulfide minerals for separate storage than the rest of the mineralization, which is more silicate nature. Because they pose different hazards and different risks and deserve to be treated differently. That's a new style of thinking. That's not how we used to do things 50 years ago, where we just put it all in the tailings pond and then try to manage the impacts. And that's why in a lot of old mining areas, you see a lot of problems with acid rock drainage, where these sulfide minerals are reacting with water and oxygen, making sulfuric acid that leaches additional metals out of the tailings, and then you get orange creeks. The Rio Tinto, the company, started with the Rio Tinto area in Spain. I mean, it's named for the Rio Tinto area in Spain, which is where the Romans were mining a couple thousand years ago. Why did they know that there were minerals there? Well, the creeks were colored. Rio Tinto, colored water, colored rivers. Because you could see that there was iron in the water because it had been dissolved by something. So you follow that back upstream and find out where it's coming from. And they found some good ore bodies. But not all tailings are made the same. Some are much finer, some are coarser. You can have tailings that are, 200 micron. You can have tailings that are 20 micron. Those will behave differently in a tailings management facility. You can have deposits that are quite rich and make a very little bit of tailings that's relatively easy to, say, dry stack or filter and stack. Maybe not dry. I've never liked the term dry stack, but you can make a filter cake and stack that up and then manage that instead of a slurry pond. But if there's a lot of sulfur in them, that's maybe not such a good way to do it, right? If you have an underground mine, they often use the tailings as part of the backfill for the mine stopes. When they're finished mining a stope out, they'll mix tailings with concrete, with cement actually, to make a mixture that they'll pump into the stope and fill it up and leave it there. And so they've disposed the tailings back underground. But when you do that, you're effectively sterilizing the area. You don't typically do it in open pit mines because you're digging deeper in the same pit. And if you try to put the tailings back in, it's in the way of your mining and poses additional challenges. So in some cases, we can redeposit it, or most of it, or some of it. In some cases, we can't, and it needs to be stored on land. The risk posed by those tailings is a really complex area that you need to consider the chemical nature of them. Some people call tailings toxic. Sure, some are not. Right? They might contain arsenic and mercury and selenium and things like that. Or they might be mostly just magnesium silicates, or they might be iron oxides, or they might be something else, right? And so the nature of the material, its chemical structure, its physical form, is it ground rock, or is it, reprecipitated from a leaching environment where you have minerals that you've made that are a couple microns in size and are therefore much more able to be mobilized and might not be chemically stable? present very, very different hazards and need to be managed very differently. And of course, how you manage them, then you get into tailings dam structures and water management and all kinds of issues around that are different from site to site. There is no best practice. Every ore should be treated like this because, every tailings facility is unique.
Yeah, and that's, I think, the important message that I'm keen to hear you explain, even if people aren't kind of following all of the polysyllabic details that you're laying out. The message that like different ore bodies are different and need to be treated differently is something that we're going to discuss kind of throughout the conversation today. And I mean, maybe I'm just simple, but when I kind of started working on mining impacts 5 years ago, I just kind of thought, okay, you're telling me that it's 2% nickel, then the rest is just rock, and the nickel is what's important. And it wasn't until I kind of started looking at flow sheets and realized that what's in that other 98% or 99.8% makes a big difference kind of for all stages. Yeah. So then, take us back to the refining stage and just kind of describe a little bit what happens after you've got the concentrated ore. How do you get that to be an actual metal that can be used?
Yeah, so typically I work in the space of nickel, copper, cobalt, zinc. We call them base metals. There's a lot of base metals, but these are the common industrial base metals. Iron's also a base metal, and these commonly occur in two forms: oxides and sulfides, or hydroxides, which are a subset of oxides, and they get treated differently, right? So I'll start first with the sulfide sides because that's really how we think of a lot of these minerals historically. How the majority of our production has been for 100 years is that we have a sulfide deposit like the South African deposits, like the Sudbury deposits, where we have a metal we want, nickel or copper or cobalt or a variety of these, in a mineral grain structure with sulfur and some other things, commonly iron. You get some other things like lead and some other stuff in there as well, depending on the deposit. And that concentrate, which will be, let's say a more of a typical copper concentrate, might be 25% copper and 25% iron and 30% sulfur, and the balance will be entrained non-sulfide minerals that are stuck along with it because we didn't break all the grains free in the mineral processing stage. That concentrate, it's valuable because it's 25% copper, so it's going to get shipped somewhere to be treated. Sometimes that place is on site, sometimes it's across the world. It doesn't matter. These metals carry enough value that they can bear the cost of shipping once you've concentrated them through that mineral processing stage. The sulfide concentrate will then typically go to a smelter or a roaster, where we burn off the sulfur and make sulfur dioxide gas and leave the metals, be they copper, iron, etc., in the solid phase or in a roaster. So for zinc, for example, you burn this at a temperature at which you still have solid zinc oxide as a product and SO2 gas coming off the top. In a flash smelter for nickel or copper, you would actually melt the ore as you burn the sulfur and get a molten phase coming out of it. So everything is melted and the SO2 comes off the top. Once you've done that, what you find is that the sulfide mineral, the remaining metallic sulfide minerals, the base metals, copper, iron, copper, nickel, zinc, etc., tend to congregate into a single phase we call a matte phase or an alloy phase that's very heavy, it's dense, it sinks to the bottom of the smelter. And on top of that, the silicates typically and any other minerals, oxide minerals, float as a slag layer, and then we tap those off separately, make a matte or alloy phase of the metals we want, and a slag phase of the stuff we don't want. And that slag can get disposed, and the metals can then go for refining. But those metals now, you're talking about something that's, say, in a nickel, copper, cobalt matte, 70% nickel, copper, cobalt, 25% sulfur, a couple of percent iron, that then still needs to be separated. So that will then go to a process where typically it's leached in an acid, hydrochloric or sulfuric acid, and you bring all those metals into solution as ionic compounds, so nickel sulfate or nickel chloride, which we can then separate chemically using a variety of processes like solvent extraction, and then recover through a reductive process where we either use electricity to make a cathode metal, pure metal, or hydrogen as a reductant to make a pure metal product out of that. And you can because you can separate the copper, the cobalt, the nickel in the liquid phase from each other, you can then make pure products of each of them coming out. Typically, some things don't like to react in the leaching process. Platinum group metals and precious metals, gold and silver, are more inert. And so they tend to go into the residues and can then be recovered from those through more extreme intensive processes where you recover each of those individually, but you're now dealing with very small quantities of those residues because you've abstracted, removed most of the mass of that material as the products you want.
Yeah, this is okay. So the way that I have eventually ended up thinking about a lot of this, and I'm just interested to hear if this is a kind of a good heuristic, but so the two things that I think tend to happen in mineral processing is reduction to metal. So I think for most people who don't think about mineral processing, the difference between an oxide and a sulfite and a metal, these are just words that describe different kind of ores, but an oxide is a metal that is attached to an oxygen. And I think of this as just like rusted metal. Like when you get iron and it rusts, then it's in its oxide form. And if you can get that oxygen molecule off of the iron, then it's back in its metal form. And this is the case for, I guess, a lot of ores, including nickel, that a big part of the process is essentially getting the oxygen off of the metal. And actually, one of the things that I also sticks in my mind is when I learned that a lot of what the Earth is made of is oxygen. Like when you see what percentage of elements comprise a rock or just the Earth generally, I think oxygen is number one and number two.
Yeah, oxygen is highly reactive, right? It's an incredibly useful material for us, right? We need it, but it is highly reactive with other things. And often what we talk about in the chemical engineering world, we talk about Gibbs free energy and all these things that describe whether something is stable or not. And for many elements, the most stable form of them is an oxide form. So iron doesn't want to be steel. It wants to be rust, right? Hematite, iron oxide. It will naturally go that way, given time and exposure to oxygen and water. Iron rusts. And we do all these things like paint it and galvanize it and stuff in order to keep that process from happening. This is why you don't tend to find sulfide ores exposed on the surface of the Earth, because on the surface, they're exposed to oxygen. That oxygen really wants to react with these metals and they want to become oxides. That's, they don't have intelligence, but their lowest energy state, their natural state, is as the oxide. So exposed on the surface, they will react with oxygen in the air and become that oxide form as they are exposed. So sulfide minerals are almost always underground, right? And so you will have, if you expose sulfides in an Arctic climate, okay, it's going to react very slowly. You might have them left on surface for thousands to millions of years because it's just a very slow reacting area. If you put it in the tropics where they get lots of water and from rain and lots of high temperatures, they react much more quickly. And so you will find different deposits in different areas because of the geologic history of the Earth and where things are. But they all want to be oxides at the end.
Yeah. Okay. So then there's this deoxidification process, the reduction process, and then there's also just kind of separation. Now you've got things in a metal form, but there are a whole bunch of them mixed together. Some of them you don't want, and the ones you want them ideally by themselves. So then you've got to try to figure out how to get the nickel away from the cobalt, away from the copper, and get the magnesium or manganese somewhere else entirely.
That's correct.
Okay. I guess the next thing I want to try to get us towards the deep sea mining question is to talk about how, like, where the impacts that we think of from the mining industry occur in this value chain. So channeling people like me before I thought about mining, tailings ponds, mining impacts, all of this is associated with mines. And then to the extent that I am aware that there's processing that happens somewhere, well, maybe there's some off gases that go into the atmosphere, or there's energy consumption. But then when I learn more about it, and then I hear about these kind of major tailings dam breaks and things, and I learn about nickel processing, and I learn that the biggest sulfur problem in the world is in northern Russia, where they're processing or refining nickel. I'm going to get you to clarify whether that sulfur is coming from. And also the problem with tailings management in Indonesian nickel is kind of actually downstream of the refining process, where it's not actually happening at the mine, it's happening downstream. So tying this into the deep sea mining discussion, like, how much of this are we really avoiding if we get marine minerals, we get them onto a boat, and then we take them to a processing facility? Are we kind of at least avoiding the dangers of some of these tailing dam breaks, or do we kind of end up actually just starting the whole risk, getting a whole set of options of problems just from a different starting point, if you know what I mean?
Sure. So, when I think about the risks and impacts of these, we go back to, the common term that's now becoming verboten in the US, ESG. What does ESG mean? It means environment, social, and governance. And we need to tear this apart to think about the impacts, just like we tear apart rocks to get the minerals we want. On the environment side, you tend to have, three kinds of impacts: land, air, and water. Land impacts will include, disturbances to the physical structure of the land, the topography. It will include impacts to the plants and animals that live there, the biodiversity impacts, those kinds of things. Those are all challenging, but occur most dramatically at the mining stage. When we talk about water impacts, those can occur along the value chain, depending on how things are managed. You have some types of water impacts at the mining stage, managing runoff, managing pit water, these kinds of things, so that we end up with an impact in the environment there that is related to how that water is managed, and whether it's still clean water from the environment, or whether it's contaminated with things from our process. But you have water impacts downstream as well in the refining stages. And air impacts typically come in most in the refining stages, because that's where we do intensive processing. So at a mine site, the air impacts are usually pretty limited, because it's related to the heavy equipment we use, the drills, the bulldozers, the haul trucks, the shovels. Many of these are fossil fuel burning equipment. They have impacts in the local environment, NOx and SOx and things like that, and they emit CO2, and that's a global problem. But many of their impacts are localized, and because most mines are remote, it doesn't affect a lot of people. If you burn a lot of diesel in a major city center, London, Amsterdam, etc., you get a lot of health impacts that you don't see if you do it remotely. When we head down the value chain, so at the mine site, we have mostly land impacts, biodiversity, those kinds of things, and that's where we tend to make tailings. And so, that tailings structure has an impact all on its own because it covers up a part of land that was not previously covered up. It impacts the water courses around it, and it has the potential, it has a risk factor of failure that is, a big deal if it happens, and, is a zero impact thing if it doesn't happen. It's a very binary situation, whereas, impacts to water quality are a very gradual situation. The air impacts, as I said, are pretty small. As we move upstream to the mineral processing, that typically occurs at the mine site. The major impact from mineral processing is the generation of those tailings to go into the tailings management facility. And it's usually a large power consumer. So for the source of that power will matter. If you're connected to a hydroelectric grid, the power will be very clean from a carbon point of view and an emissions point of view. If you have a coal-fired power plant or a diesel-fired power plant, you'll get a lot of emissions of not just CO2, but also the NOx and SOx and other things. Again, it tends to be remote, so those local air pollutants that would create smog are less damaging than if they were in a major urban center. In the mineral processing, you're effectively putting the tailings out to be managed, and you're taking the concentrate away. When you get into the refining stage, now you're into intensive chemical processing. You have a large number of reagents often. You use acids and bases and other things. You use often organics for solvent extraction. You tend to use a lot of electrical energy as well. Sometimes you're using oxygen or hydrogen, which are made from oxygen from electricity, hydrogen usually from fossil fuels. And so all of these have both direct and indirect impacts at the refining location, which is sometimes a fairly urban location, right? The Sherritt refinery that I used to work at is within the civic boundary of the city of Fort Saskatchewan. It was about less than a kilometer from the refinery to the nearest houses. So we had to be very cautious about our potential impacts on local citizens. So, the release of a toxic gas would be a very big deal for the local citizens, where you had a remote operation, not so significant. As you said, the largest anthropogenic SO2 source, sulfur dioxide source in the world, is a nickel smelter in Russia, nickel copper smelter. Puts out a lot of SO2 because it's not economic to capture it and take it somewhere else as a byproduct sulfuric acid, which is what they do at a lot of other smelters, such as Sudbury in Ontario, where both Glencore and Vale make sulfuric acid, and that goes as an industrial product, useful industrial product to customers within the area, and you have greatly reduced sulfur emissions from what it used to be 50 or 70 years ago. As emissions regulations have tightened up in countries like Canada, we've seen smelters close, right? Flin Flon used to have a zinc roaster and a copper smelter. Now it has a zinc pressure leach plant, which has no SO2 emissions and no copper smelter. Thompson in Manitoba, no nickel smelter anymore, because it wasn't economic to capture the sulfur dioxide from those, and the government regulations required emissions be below a certain level, and so the facilities were simply turned off.
Yeah, this is another place where I think emphasizing the complexity of the decisions that kind of have to get made is worthwhile. So in the Russian example, it's not that they can't capture all that sulfur. The problem, as you've explained it to me before, is that if they capture it, they could sell it, but it's just too far to transport it to a market. So it's actually just kind of a logistics question as opposed to a technology question or a regulatory question for that matter.
Yeah, that's correct. I mean, if you put that smelter in the middle of Germany, that sulfuric acid would find a use in Western Europe. But it's in northern Russia, mid-continent, very close to the Arctic coast. And it's not economic for them to ship acid out of there as a byproduct. They have another option, which is make the acid and react it with something like a limestone to make a disposable sulfate residue like gypsum. There's other minerals you could use, but that's just a cost, right? You're not making a byproduct that you can make some money off or even cover its cost of production. You're simply incurring a cost. So, as any corporation in the Western world would do, you don't incur a cost you don't need to. So, they've been talking about sulfur recovery for a long time. I understand that they're partway through a major capital project to recover some of that sulfur. Time will tell when that happens and how much it is. You'll never capture it all, right? The reality is that there will always be some emissions because you can't completely clean the SO2 out of the air, but you can get most of it. So in Sudbury, Inco, then Vale now, has spent over $1 billion on its air emissions reduction programs over the last 50 years to reduce the amount of SO2 going to the atmosphere. And if you went to Sudbury 50 years ago, it kind of looked like a moonscape because the acid rain from it created a lot of vegetation damage. Today, it's a beautiful city. Sudbury's got a lovely area. I've camped in that area. It's gorgeous nowadays. That's testament to the work that's been done under the force of government regulation, well enforced, to make sure that those emissions are reduced in an economically viable fashion.
Okay, thank you for listening. You can find the second half of this conversation with Lyle Trytten, previously published in the podcast library. In the second half, we discuss tariffs and the difficulties ahead for building out mineral processing capacities. You can follow Lyle on LinkedIn, where he actively posts about all things decarbonization and minerals. He also posts a lot of great white papers or expansive blog posts. I really advise listeners to go there and check out his series on sustainability in the resource industries. Lyle is updating a series of posts that he originally wrote years ago, and I'm getting a lot of value out of reading them as they are re-released. Thanks for following the Elements of Deep Sea Mining. If you like the show, please do share it with others who might be interested. And if you have suggestions or guest recommendations, please share them with me. You can find my email in the show notes.
I throw my arms up and to the side.